The ideas of dark matter and dark energy obviously play an important role in modern cosmology. They've made everything fit together in the sense that a whole bunch of data of a whole bunch of different kinds of phenomena suddenly make sense if you believe that only 5% of the universe is ordinary matter, 25% is dark matter, 70% is dark energy. It's an impressive amount of data, and it's not just the same kind of phenomenon over and over again. It's a wide variety of different things that we're looking at that convince us that 95% of the universe is this dark stuff, this dark sector. So physicists naturally are very excited about what this stuff is, what its properties are. People are buying series of lectures trying to understand where this stuff comes from and what it might be. However, we have to keep in mind that every single piece of evidence that we have that points that they're in the direction that there are such things as dark matter and dark energy come from measuring gravitational fields. We do not find dark matter and dark energy yet directly in our laboratory. We hope to do that, and we're trying to do that, but so far it's all been about inferring the existence of dark matter and dark energy on the basis of the gravitational fields we observe in the universe, on the basis of the way in which space and time are curved, and we attribute that curvature to stuff. We can attribute it to a bunch of cold, massive particles called dark matter, and a smoothly distributed, nearly constant kind of stuff in empty space called dark energy. However, logically speaking, it's certainly possible that our inference is incorrect because the theory of gravity that we're using to relate observed gravitational fields to the stuff that causes them is wrong. That theory of gravity, of course, is Einstein's theory of general relativity. So in this lecture, we'll dig into the possibility that general relativity is not right. Certainly general relativity is pretty close to being right, both in the solar system, where we've tested it very well, and in other more local things in our galaxy, like the binary pulsar, a pair of two neutron stars which is changing its rate of rotation due to emitting gravitational waves, just like Einstein predicted. In other words, we have a lot of empirical data saying that general relativity is a pretty good theory on scales of several astronomical units, 1 light year across or less. But now, in cosmology, we're looking at the whole universe. We're looking at many millions of light years across, many billions of light years across. It is certainly possible that gravity acts differently on length scales of billions of light years than it does on the scale of 1 light year. Can we do better than Einstein? Can we come up with a better theory than he did that will explain how gravity works on large scales and fit the data without invoking dark matter or dark energy? I should say that Einstein, of course, is a famous physicist, and he's a very smart guy, but even though his theory is very good, there is nothing sacred about it, and therefore there's nothing sacrilegious about questioning general relativity. There's a feeling that some people have that we establishment cosmologists have as our duty to defend Einstein's honor against attacks from talented but quirky outsiders. Nothing could be further from the truth. Any working theoretical physicist would like nothing more than to be the one who came up with a better theory of gravity than Einstein. That's why we all got into the game, so that we can have a better understanding of nature, something that goes beyond what we already have. Furthermore, we all believe that general relativity is not the final true answer. We all expect that general relativity needs to be modified in some way, if only because general relativity as we currently understand it is completely inconsistent with our understanding of quantum mechanics. That's the problem of quantum gravity, which we'll be getting to in a later lecture, that string theory has been proposed to resolve, but it tells us that general relativity is at best an approximation. It can't be the final correct answer because the world is not classical and general relativity is. Therefore, maybe general relativity is also wrong on larger scales. That's not what we would expect. Usually in physics, if we understand something at a different physical distance, we will also understand it at larger distances. New things will kick in at smaller distances where energies become larger and quantum mechanics becomes important. But logically speaking, it is a possibility, so we're all very, very interested in wondering whether or not our current inference about dark matter and dark energy could somehow be traced to a misunderstanding of how gravity works. Before we go into details, it's worth telling this very amusing parable, this story about how people have already tried this game and how we get ambiguous results from looking at the historical record. Most of what we know about gravity, both even today as well as in the past, comes from the dynamics of stuff in the solar system. the different satellites around the planets, and the planets moving around the sun. So everything moves in a gravitational field. This is how Kepler was able to find out that the planets move in ellipses rather than in perfect circles. And from Kepler's understanding of planetary motions, Isaac Newton was able to derive his inverse square law for gravity. The idea that the force, the gravitational force between two objects, decreased inversely as the distance squared. However, this theory of Isaac Newton's, even though it fit the data of the planets very, very well, didn't always fit perfectly. The first time anyone discovered a new planet since ancient times was the discovery of Uranus in 1781. It was discovered with a telescope, a brand new planet out there, once again, evidence that the heavens were not fixed and given to us ahead of time. We had to go out there and look to see what would be there. So people were very excited about this. They took many different observations of the motions of this new planet, and they tried to ask whether or not Uranus fit into what we understood about the solar system. Interestingly, the motions of that new planet were not precisely those that you would have expected, given the laws of gravity as they had been handed down by Isaac Newton. So what do you do when there is an object in the sky whose dynamics are not exactly what you would have predicted on the basis of the gravitational fields you think are there? You invent dark matter. You invent some new stuff that you haven't directly seen, whose gravitational field is influencing the motion of the things you do see. So the French mathematician Urbain Le Verrier invented a new planet, which we eventually called Neptune. He predicted exactly where Neptune would have to be located in the sky in order for it to be pushing around the orbit of Uranus in the right way. And when he finally convinced people to go look for it, they found it to within 1 degree of where he predicted that it was on the sky. This was the first example in history of where a dark matter hypothesis was presented and turned out to be right. Of course, once you see it, it's no longer dark matter, but we're hoping to do exactly the same thing with real dark matter and real dark energy. Then it was realized within Le Verrier's lifetime that there was also a problem with the inner planets. The motion of Mercury, in particular, was not precisely what Isaac Newton said it should be. Mercury moves in an elliptical orbit, and that ellipse was known to precess, to change its orientation gradually as a function of time. Now, part of this precession is just due to the fact that the solar system is not a pristine place. There's more to it than just the sun and Mercury. The sun is rotating itself, which gives it a different kind of gravitational field, and of course there are the other planets. So Le Verrier, fresh off of his success at predicting dark matter and discovering Neptune, did the same trick again. He proposed that there is dark matter in the inner solar system, in the version of a new planet called Vulcan. So Vulcan would be another minor planet in the solar system inside the orbit of Mercury. Le Verrier predicted exactly where it should be, and lo and behold, it was discovered. In fact, it was discovered more than once. All of these times it was discovered turned out not to be right, because of course there is no planet there. In the case of Mercury, the reason why it's not moving in the way that Isaac Newton predicted that it should is because Isaac Newton isn't right. Because gravity doesn't quite work the way that Newton said it does. There are slight deviations, and those deviations were finally understood when Einstein came along and made his general theory of relativity. After Einstein invented general relativity, one of the first things he did was to check what it would predict for the orbit of Mercury, and he found that it exactly accounted for the discrepancy between what was observed and what was predicted. This, Einstein said, was the happiest moment of his life when he realized, before anyone else in the world did, what the correct explanation was for the motion of Mercury. So what is the lesson from our little story? We can see that things move through the heavens. We can use them to predict the existence of stuff based on our understanding of gravity. Sometimes that prediction turns out to be right. Sometimes we do understand what gravity is doing, and we successfully infer the existence of new stuff. Sometimes it's because gravity is the culprit. So we can try to do exactly the same thing now. We can try to use a new theory of gravity to try to explain away dark matter and dark energy. As one final bit of caution, we should notice that in the solar system, the place where the dark matter hypothesis worked was in the outer solar system. The place where we didn't understand gravity was at shorter distances, at smaller length scales. So the fact that we understand gravity right now very, very well in the solar system suggests that we probably understand it in the galaxy and in cosmology. But once again, because the very discovery of dark matter and dark energy has been such a surprise, we're trying to keep an open mind and to see what will happen. So the evidence we have for dark matter and dark energy takes very different forms for those two different things. We believe that dark matter is something local, something that falls into places where there is ordinary matter, into galaxies and into clusters, and increases the strength of the gravitational field. It's a fairly simple idea to try to get rid of dark matter with a modified theory of gravity. The fact that you have a galaxy or a cluster and you measure its mass by looking at the motions of things near the edge and you find too much could potentially be explained by the simple hypothesis that the force due to gravity is stronger at large distances than you thought it would be. In other words, it falls off more slowly than 1 over r squared that Newton would have you think. That's the kind of thing you would need to make work if you want to replace dark matter with modified gravity. Dark energy, on the other hand, is smooth and global. It does not collect into galaxies and clusters. It is all over the place. Furthermore, it does not pull things together more strongly like dark matter does. It is pushing the universe apart. The first manifestation of dark energy was that the universe is accelerating at a faster and faster rate. So to get rid of dark energy rather than dark matter, what you need to do is to find something that makes the universe accelerate and something that is not associated with any given kind of source, something that is all over the place, not collected in the area where there is ordinary matter. So the attempts to do away with dark matter and with dark energy by modifying gravity seem to have a different character. Maybe they're the same modification, or maybe they're the two different modifications. Maybe there is dark matter but not dark energy, or vice versa. All of these possibilities are there on the table. So let's think in more detail about the dark matter case. What do we actually know? What is our evidence for dark matter? The original evidence, of course, came from clusters and from individual galaxies. We would look at the dynamics of these systems. We would look at stuff moving around galaxies, for example, use that stuff to infer the total amount of mass. We would look at the motions of galaxies, use the velocities at which they're moving to infer the total amount of mass in a cluster of galaxies. These days, we have slightly more sophisticated forms of evidence that are slightly less direct. We have the cosmic microwave background. The different splotches in the microwave background respond to the existence of dark matter, and that's more evidence that there's more in the universe than just ordinary matter. We have the evolution of structure in the universe, and for that matter, we have the fact that the universe is spatially flat, which relies to some extent on the existence of dark matter. Now, it's kind of remarkable that the one hypothesis of dark matter particles can fit all of those different phenomena. And it would be very difficult to imagine coming up with a new theory of gravity that did just as well. But we can start with a simple starting point. Forgetting about trying to explain everything at once, let's just take one phenomenon and try to explain that. So this was done in 1984 by Mordecai Milgram, who said, let's just look at the rotation curves of spiral galaxies. Remember, the rotation curves of spiral galaxies were measured by Vera Rubin in the 1970s and were the first really quantitative evidence that most of the stuff in the universe was dark matter, not ordinary matter. She measured the velocity of different kinds of stuff as you went from the center of a galaxy to the far edges. If what you saw in the galaxy was what there was, that velocity would fall off as you got further and further away. What Rubin found was that that didn't happen, that the velocity stayed nearly constant, evidence that you needed dark matter in the outskirts of the galaxy to make the rotation curves make sense in the context of Newtonian gravity. Milgram noticed a very interesting fact about the universe, and regardless of whether or not he's correct about modifying gravity, this fact remains true. The fact is that if you look at different galaxies, measure their rotation curves, and look at where you need dark matter and where you don't, you find that in the centers of galaxies, you don't need to imagine that there's dark matter. Maybe it's there, but the ordinary matter is enough to explain the motions that you observe. It's only in the outskirts that the effect of dark matter builds up enough that you absolutely need to imagine that it's there to explain the data. Now, the radius of the region where ordinary matter is enough is different for every galaxy, and everyone knew that. But what Milgram noticed was, if you calculate, just using the laws of Isaac Newton, the acceleration due to gravity at the point where ordinary matter is no longer sufficient, with the point where you need to invoke dark matter to explain the motions, that acceleration due to gravity was the same in every galaxy. There was some crossover value of the acceleration, such that when the acceleration due to gravity was larger than that value, you didn't need dark matter. When it was smaller, you did. So what Milgram said is that maybe the point is that there isn't any dark matter. Maybe there's a new theory of gravity. Maybe the theory of gravity that is correct has the property that if the acceleration is greater than a certain value, it's a 1 over r squared inverse square law, just like Newton said. But at smaller values of the acceleration, gravity has a force that is stronger than that. It falls off more gradually, like 1 over the distance, rather than the distance squared. Well, whether or not that's true, it fits the data very well, not only for the galaxies that Milgram knew about when he was making this hypothesis, but for new kinds of galaxies that were discovered after he made it. For individual galaxies, Milgram's rule of thumb, that you don't need dark matter and Newtonian gravity works in the insides, and there's a very specific radius outside of which you can fit the data by modifying gravity, fits over and over again. This is a remarkable fact about the universe. Maybe it's because there's modified gravity. Maybe it's because cold dark matter arranges itself so that that will be the case. If the latter possibility is right, it's a challenge for the theory of cold dark matter to predict why this observed fact found by Milgram seems to be so true in the real world. The problem with Milgram's theory, which is called modified Newtonian dynamics, or MOND, the problem with it is that it's not a theory. It's a suggestion for one very specific circumstance, for the rotation curves of galaxies. But we know there's more to the universe than galaxies. There are clusters of galaxies. There's the expansion of the whole universe. There are more phenomena than rotation. There are galactic gravitational lenses, for example. How can you make predictions for all of these observed phenomena from Milgram's theory? The answer is you can't. You need to take that suggestion that the law of the fall off due to the gravitational force is different than Newton's and embed it in a more comprehensive framework from which you can make better predictions. Even before you do that, the one thing you can do is to try to go from galaxies to clusters of galaxies, and what you found over and over again is that it doesn't work. Milgram's modified rule works very, very well for individual galaxies, but when you start including clusters of galaxies, you could make a prediction, and the prediction did not come true. People tried and tried to understand clusters of galaxies better and better within Milgram's framework, and they never quite succeeded. Eventually, they more or less gave up on the idea that you could explain clusters of galaxies purely by modifying gravity, at least with Milgram's idea. The people who are now proponents of MOND, proponents of Milgram's idea, believe that in order to explain clusters of galaxies, there has to be some dark matter there. However, they say that the dark matter that is in clusters of galaxies might be different than the kinds of dark matter you imagine in conventional concordance cosmology. For example, the dark matter that is in clusters of galaxies could be neutrinos. In ordinary cosmology, we don't think the dark matter can be neutrinos because neutrinos are hot dark matter. They move very quickly. They don't settle into galaxies and make them form. In a universe dominated by neutrinos, structure would be very, very featureless. But they do move slowly enough that they can be captured by clusters of galaxies. So basically, people who believe in Milgram's theory have retreated to a position where clusters of galaxies are explained by dark matter, but individual galaxies are explained without dark matter by a modified theory of gravity. Still, it wasn't until 2004, 20 years after Milgram's original theory, that Jacob Bekenstein finally managed to come up with a full theory that reduced to Milgram's idea in the appropriate circumstances. You'll not be surprised to learn that Bekenstein's theory was very complicated. It's not easy to come up with a modification of gravity that fits all the data. So Bekenstein's theory invented new fields. That's what you do whenever you invent a new theory of anything. You add new fields and see what they do. He added a bunch of new fields. He found that he could predict what Milgram predicted for the cases of individual galaxies, but you could also fit other cosmological data. Remarkably, Bekenstein's theory fit things like the microwave background and the acceleration of the universe if you not only put in the neutrinos you need to explain clusters, but also you put in dark energy. So on the one hand, you finally had a model of modified gravity in which individual galaxies did not have important amounts of dark matter in them. But other than that, it was a very conventional model. Clusters of galaxies and the whole universe are defined by dark matter and dark energy. So even though that kind of model fits the data, the people who were originally enthusiastic about it have lost a certain amount of motivation. Originally, the hope was you were getting rid of dark matter entirely. Now you're just getting rid of non-standard model dark matter, hoping that it can be neutrinos, but the motivation for doing that is a little bit less. But it still could be true. Let me back up a little bit from the notion of Milgram's particular proposal to the general notion of doing away with dark matter in galaxies. And let me mention my belief that you absolutely need some kind of dark matter in the universe. It is impossible in principle to think of a theory in this day and age which will completely do away with dark matter. And there are two pieces of evidence for that. One is, of course, the bullet cluster. We talked about the bullet cluster when we talked about the original evidence for dark matter. Here you have two clusters of galaxies that pass through each other. The hot gas that is most of the ordinary matter got stuck in between, and the galaxies and dark matter went right on through. When you look for the gravitational fields of these clusters using gravitational lensing, you find that most of the gravity is being caused by the dark matter, not by the ordinary matter that got stuck in the middle. If you're going to modify gravity in a way to get rid of dark matter, typically what you will do is you will modify the strength of gravity as a function of distance. But it is very hard to modify the direction of gravity. If you're trying to come up with a model in which there is no dark matter, the only source for gravity is the ordinary matter. The only plausible direction for which the gravitational force can point in is toward the ordinary matter. But the bullet cluster is a very clear-cut example where we have a gravitational field that is pointing in a direction other than where the ordinary matter is. The bullet cluster makes perfect sense if there's dark matter. It's very hard to understand if there's no dark matter and gravity is modified. Similarly, you have the cosmic microwave background. We told a story about the oscillations of overdense regions in the early universe, and how sometimes they were in phase with the dark matter, sometimes they were out of phase, and that is precisely what you observe in the cosmic microwave background. If there is no dark matter, if there is just modified gravity, then there isn't anything to be in phase with or out of phase with. It becomes correspondingly much, much harder to explain what we see in the cosmic microwave background. These are both very general arguments. They don't attack any specific proposal, but what they say is that we have very good evidence that there isn't any specific proposal that you can possibly come up with to do away with dark matter and replace it by modified gravity. You never know. It's not a theorem that is absolutely rigorous, but it's pretty good evidence that dark matter really does exist. So what about dark energy? Dark energy is very different than dark matter. Among other things, it's much simpler, or at least we know much less about it. Dark matter clusters together, it has dynamical properties. Dark energy might be dynamical, but the only thing that we know is that it's a nearly constant energy density, enough to make up 70% of the critical density of the universe. So what you want to do to modify gravity to get rid of dark energy, in other words, imagine the dark energy is zero, but there's some modification of Einstein's equation that makes the universe accelerate, is ultimately to modify the Friedmann equation. The Friedmann equation is the one that tells us how the expansion rate of the universe responds to energy density. And it tells us that if the energy density goes to zero, the expansion rate goes to zero along with it. If you want to do away with dark energy, you want to modify the Friedmann equation in such a way that as the energy density goes to zero, the expansion rate stops going to zero. Either it goes to zero much more slowly than the energy density does, or it actually gets stuck at some finite value. The important thing to realize here is that there are constraints on what you can do. Just like with dark matter, there are plenty of experimental constraints. For dark energy, where we want to modify the Friedmann equation, there are some things we know about the Friedmann equation. For example, we know it works very, very well in the early universe. The Friedmann equation is tested to very good precision by both primordial nucleosynthesis and by the cosmic microwave background. We have two sets of phenomena which, if you try to explain them on the basis of the Friedmann equation plus ordinary matter and radiation, you get exactly the right answer. If If you try to modify the Friedmann equation, for example, try to imagine modifying the Friedmann equation so that the universe is always accelerating, you would be dramatically in disagreement with the predictions from nucleosynthesis and from the microwave background. All of the data that we have today are telling us that the acceleration of the universe is a recent phenomenon, cosmologically speaking. When the universe was half its current size was the time when the universe was going from decelerating due to the matter and radiation in it to accelerating due to the dark energy. So if you want to modify the Friedmann equation, you modify it in such a way that the modification turns on relatively late in the universe's history. So here's the problem with that idea. It can be done, but there are issues that you need to face up to. Here's Einstein's equation again, telling us that the curvature of space-time on the left is related to the stuff in the universe on the right. You want to modify this equation. You want to modify this equation such that when the stuff goes away, there is still space-time curvature. Even if there's no energy density, even if the universe expands and dilutes away all the matter and radiation, space-time curvature will not go to zero. That is your goal. The problem is that this equation of Einstein's is actually quite remarkable. If you try to mess with it just a little bit, you break it, basically. What we mean by this is if you try to add terms to Einstein's equation that are small, they give rise to some discrete new effects. In particular, they turn on new fields. We mentioned very, very briefly that gravity, the force due to gravity, in a quantum mechanical context, can be thought of as being due to the exchange of gravitons, spin-2 massless bosons. But if you change Einstein's equations in any relevant way, there are more particles than just gravitons. There are new kinds of particles that qualify as part of the gravitational force. And those particles have an effect. So what you're trying to do is to mess with Einstein's equation just a little bit, just so that it is important in cosmology, late times when the universe wants to begin to accelerate, but is completely irrelevant here in the solar system. What you find is that that's much harder to do than you thought. At least the simple things you do have a very interesting effect. We test general relativity in the solar system, and we can ask whether or not the fields that are there, the fields that are affecting the space-time metric, are the ones that we're observing. So, this is a picture of the Cassini probe, a satellite launched by NASA which nominally had as its job to take pictures of Saturn and Jupiter and the other outer planets, but along the way did us a favor. Cassini beamed signals from itself to us here on Earth as it was passing through the path of the sun. So we had the sun, and behind the sun was the spacecraft. It passed signals to us, and one of the predictions of general relativity is that time is warped along with space. As a result of this, the time it takes that signal to get to us is delayed by the gravitational field of the sun. Because we know exactly where the satellite was, you need to plan out its trajectory to very high precision in order to get it to Saturn correctly. We can do a very good job of measuring that time delay, and it turns out it was precisely what general relativity predicted. What this means is that there aren't any new gravitational fields in the solar system of the kind you would predict if you tried to mess with Einstein's equation. For whatever reason, Einstein's equation is very, very true in the solar system. But the rule that we have is that if you want to change something on large scales, it's very hard not to change them on small scales. No one has been able to come up with a nice theory where we are able to change Einstein's equation to make the universe accelerate at very, very late times without modifying the dynamics right here in the solar system. You might expect it was possible, but we haven't been able to do it yet. On the other hand, to take these lemons and to make lemonade, by thinking about these theories, we've been inspired to a new way to test general relativity. What we have in the case of dark energy is an accelerating universe, and from the dark energy hypothesis and the amount of acceleration we observe, you can make predictions for how structure should evolve as the universe gets bigger. We have an early universe which is very smooth, small perturbations in energy density from place to place, which you can see in the fluctuations of the cosmic microwave background. And under the force of gravity, those fluctuations grow into large-scale structure today. You can see in this map from the Sloan Digital Sky Survey the distribution of galaxies across the sky. those come from the tiny ripples that we see in the microwave background. The equations that relate the early tiny ripples to what we see today are, of course, Einstein's equation. So the point is, if you mess with Einstein's equation to make the universe accelerate, you will also be changing the equations that make structure grow. So if you try to calculate the effects of dark energy on both the acceleration of the universe and on the growth of structure, and then you go out and observe those two things separately and find that they are incompatible, it is possible to explain that incompatibility by imagining that gravity has been modified. Or, turning around the same logic, if you find that the same exact dark energy theory explains both the acceleration of the universe and the evolution of structure, then Einstein was right. So right now we're trying to do this. This is one of the things that cosmologists are embarked on as we speak, to try to measure not only the expansion of the universe using supernovae, standard candles, but also the evolution of structure in the universe. If you get a consistent picture by imagining that there is Einstein's equation correctly and dark energy and dark matter, we'll know that Einstein, who was very smart after all, will probably be having the last laugh.